All right, logarithms. Logarithms are really just another way of writing an indices. So you can change from index form to log form and vice versa using this definition here. And it's really, you kind of go like around in a circle. Notice both in index form, a is called the base, and in log form, a here is the base. And so if you should go from log form to index form, you draw a circle. A to the power of x equals y. And you see that's what we have here. A to the power of x equals y. So a to the power of x equals y. So a logarithm of a number y to base a is the power to which a must be raised, there it is, to give y. So x is called the index, the power or the exponent, and a is called the base. So logarithms are just another name for the index or power of a number. You know, that was the index or power, and in log form, that's what it is. Two important results. Log of a base a is equal to 1. That's because a to the power of 1 equals a. And log of 1 base a equals 0. That's because a to the power of 0 equals 1. So let's write these statements in log form. Okay. So in this first example here, the base is 2. So we'll also have a base of 2 in our log. And it is 2 to the power of 4 equals 16. So really it's log of 16, base 2 equals 4. And you can check that, remember, by doing the circle. 2 to the power of 4 equals 16. There we have it. In this next example here, we've got log. There's our base 5. And it is 5 to the power of 1 equals 5. And there we have it. So this is 5 to the power of 1 equals 5, which is what we had there. Or log of 5 base 5 equals 1. Okay, and that's this rule up here. So log of any number with the same base always equals 1. Because you know any number to the power of 1 always equals that same number. Okay. In this next example, 3 is the base. So we're going to have log base 3. Oh, I better leave a bigger space there. And we've got log of 3 to the power of 2 equals 1/9. So there we have 3 to the power of negative 2 equals 1/9, or the log of 1/9 base 3 equals negative 2. So going from index form to log form. And the last one here, we have a base of 12. So that's log base 12. It's 12 to the power of 0 equals 1. So now circle 12 to the power of 0 equals 1, which is what it is in index form, or log of 1 base 12 equals 0. And that's this other important result. Log of 1, doesn't matter what the base is always 0, because anything to the power of 0, as you can see, is always 1. Oops. Okay, use the definition of the logarithm to evaluate each of the following. So we really want to find, to evaluate this log, we'll let it equal x, and then we can just change from log form to index form. 2 to the power of x equals 32. Now you know with solving exponential equations where the exponent, where the x is the exponent, that you want to get the same base on both sides. So we can change this. We can change 32 to, I think that cut out there, so 2 to the power of 5 equals 32. So now we have an equation with the same base on both sides, which means the exponents must be equal, so x must equal 5. And remember, x was log of 32 base 2, so log of 32 base 2 equals 5. And you can see that in index form, 2 to the power of 5 equals 32. Yeah. In this next example here then, we'll let that equal, let log of 81 base 27 equal x. So in index form, that's 27 to the power of x equals 81. So we want to get the same base on both sides. So let's change 27 into 3 cubed. And let's change 81 into 3 to the power of 4. Then we've got 3 to the power of 3x using our index laws, our powers of powers, multiplying 3 times x, and equals 3 to the power of 4. Then we've got an equation that has the same base on both sides. The base is 3, which means the exponents must be equal. So 3x must equal 4. So x must equal 4 on 3. And just run out of space here, so that's what we can say. Log of 81 base 27 equals 4 over 3. Now, on your calculator, you'll see a couple of different log buttons. The logarithm, your calculator only works out logs to base e and base 10. When you see the ln button, which is like that, that means it's log base e. Or if you see it written like that, log base e, then it's obvious it's base e. And if you don't see it written with any base, then it generally means that it's base e, which means the natural log. So that's the button there that you'll see on your calculator. It looks like IN, but it's LN, standing for natural log. The L there in natural. The other log button on your calculator, though, that is base 10. Okay, so there's the base 10. Okay, and that's the button that you would use if you were trying to find base 10. So for those previous two questions that we did, base 27 and base, can't remember what the other one was, you can't do those on your calculator because on your calculator it's only base E and base 10. But we are going to learn a little bit later how to do a change of. So now let's sketch y equals log x. Okay. So, and state the domain and range. Oh, do you remember doing that when we did functions? So, the sketch of y equals log x is actually like this. The x-intercept there is 1. On the same sketch set of axes, sketch y equals log of x base 10. So I'll just change colours, and in purple now I'm just going to draw y equals log base 10. So also the x-intercept is going to be the same general shape, and there's obviously a asymptote here. It never touches the y-axis down here, even though my little arrowhead looks like it is. Not the best graph I've ever drawn. So in purple we've got log of x base 10, and in blue we have log of x base e, both having the same x-intercept there. Using a different colour sketch, the gradient function. So remember we've done a little bit on gradient functions now. The gradient function is the first derivative, and the gradient function of log of x base e. Alright, now you can see this gradient the whole way is positive. Is very positive right here. It's very steep, and as x approaches infinity you can see it's still positive, but it's getting less steep. So that means our gradient function is going to be above the x-axis because it's going to be positive the whole time, and it's going to start off steep and get less steep. So our gradient function is going to look something like this. And that looks like a familiar graph, doesn't it? So that's the gradient function. So what do you think the gradient function looks like? What graph do you know that looks like that? Well, it looks like part of a hyperbola, doesn't it? It looks very similar to y equals 1 on x in the first quadrant. So the shape of the gradient function is a hyperbola. And so when we start differentiating log functions, please remember that the gradient function is a hyperbola.